Okay, so now we'd like to walk through a couple of the sorts of problems we're going to have to do to solve circuits. So to start with, we just have a simple one. So this is showing two different circuits with two light bulbs and one battery. And our question is, which circuit is wired in parallel? So it's useful that we be able to identify which circuits are series and parallel because it helps us solve the circuit. So that's all we have to do here. So, alright, in A, if we are following our current is going from the positive terminal to the negative terminal. I guess the electrons go the other way, but in any case, the point is that the current goes through the first light bulb, then the second light bulb, then to the battery, so that's in series. In the case of B, then if we go to the positive terminal here, so then our current, part of the current flows through light bulb 1 and then to the battery, and part of the current flows through light bulb 2 and then to the battery. So that means there are two separate paths that the current is following, so that means that it is in parallel. So our answer here is B is in parallel. The next one is what happens if only a wire is attached between the positive and negative ends of the battery. So I don't know, if we snuck in and we added a wire here. So if we did that, well, what would happen? Well, the resistance of this wire, we're considering that to be effectively zero. So if we're trying to find the current, we know the voltage of the battery, the resistance is zero, so that means you would divide the voltage by zero to get the current. So you're not really supposed to divide by zero, that's a problem. So what's happening is basically you're pushing as much current as possible as you can through this wire. This is what's called a short circuit. And what happens there is basically all of the current will flow through that wire. It's going to get hot in a hurry. It's probably going to start to damage things. One case where you hopefully don't run into a short circuit is if you drop your phone into the water. So what happens? Well, there are all these microelectronics in your phone, and so the water is a good conductor. So the result is that you get a whole bunch of these little short circuits. So you want to get that water out of there as quickly as possible, or you might have some problems. So in any case, so that's what's going on if we have a short circuit. So here we've got some conceptual questions about three identical light bulbs. So in our first one, three identical light bulbs are connected in series to a D-cell battery, and we want to know what is the voltage on each light bulb. So when we are working in series, what happens is the current through all of the light bulbs is the same. So current here, current here, current here is all I. Now we're told that these light bulbs are identical, so that means their resistance is also identical. So that means R1, R1, R1. Since R1 is equal to R2 is R3, I'm just going to call it R1 in this case. So anyhow, so that means that the voltage drop across each of these is going to be equal to the current times R1. So that means if we add it up, so V total is equal to V1 plus V2 plus V3, and since they're all equal to each other, that means it is equal to 3 times the voltage of 1. And so if we plug that in, we know that the voltage is 1.5 volts because of the battery, so we divide by 3 and we get the voltage is 0.5 volts. So really, as long as you know that the light bulbs are identical and that they're all in series, so their voltage drops are the same, then that means, well, if 3 of them are all the same, they add up to 1.5, then that means each one has to be 0.5 volts. Now notice, if they're in parallel, then the voltage drops are all the same. So here we've got 3 identical light bulbs, and they are connected in parallel to a D-cell again, and then we want to know what is the voltage on each light bulb. This one, well, the voltage drop across the parallel is just the voltage across the whole thing, right? So essentially, the voltage here, voltage here, voltage here, that's all equal to the voltage across the battery. So it's going to equal 1.5 volts. That's because when you have resistors or light bulbs here in parallel, the voltage across them all is the same. So since that's the only thing in the circuit, so the voltage drop has to be 1.5 volts across the parallel. Now, if we asked you about current, then in that case, then because the resistance is the same, a third of the current would go through each of these individual light bulbs. So that would be, the resistances were different, then it would be more complex. But the point is, the voltage is all the same in parallel, and the currents are different. Straighten it up. All right, so here we've got sort of classic sort of problem where we have both series and parallel at the same time. So in this case, we're doing capacitors. So in this case, we are given the capacitance of our three capacitors here. So C1 is 60 microfarads, C2 is 10 microfarads, and C3 is 10 microfarads. And we are asked basically what is the equivalent capacitance between points A and B. So this is what we call solving a circuit. And so how do we do this? Well, what we need to do is we need to find two capacitors, or if this was resistors, two resistors that are either in series or parallel, so we can simplify them. So in this case, all right, let's say we want to find something in series. Well, C1 and C3, are they in series? Well, not really, because there's also a path of C1 to C2, so that means that basically all of the current through 1 is not equal to the current through 3, so that means that this does not count as being in series. On the other hand, do we have a pair that's in parallel? So that's C2 and C3. So C2 and C3, they are in parallel. The voltage drop across these two capacitors is exactly the same. So that means that they're in parallel, so we can just simplify their section of the circuit and solve for them. So these are capacitors, and they are in parallel. So C2 plus C3 is equal to 10 microfarads plus 10 microfarad. So C23 is equal to 20 microfarads, right? It's they're in parallel, so this is capacitance, so we just add them together. So that means we can rewrite this 60 microfarads, 20 microfarads, and this is an equivalent circuit to the one we just did. So now we've got two capacitors in series, so 60 microfarads and 20 microfarads. So now we can solve for this. So to do that, it is 1 over C total, 1 over C60 plus 1 over 20. So do I have room here? So to solve this, you would do 1 over 60 plus 3 over 60, which is equal to 4 over 60. And so that means you flip it, so C total is equal to 15 microfarads. Okay. So yeah, so that's how you solve this. And so if it was resistors, you'd do the same thing, except the C2, they would be, you'd have to do different formulas to solve for them, but you'd do the same concept. You would solve for these two in parallel, and then you would add whatever the result of this in parallel is to the other resistor that's all in series with it. Okay, so yeah, so then our last one here is some of our cut wire problems. So these are always kind of fun. So the question here is, which wire would you cut to turn on bulb A? So let's look at our circuit here. So what's going on here is we've got our current, and so basically our current wants to follow the voltage, and what you'll notice is that here and here, the loop that has A in it, basically there's no reason for the current to go through that, because it can go directly here or it can go through here. I guess if you're being technical about it. So this is a parallel circuit where one resistance is 0 and the other resistance is something. So the result is all of the current will just go through the wire G, and then it will continue and go through light bulbs D and B. And so these two light bulbs, B and D, will be on, but and A will be off. So, and if you wanted to turn on bulb A, what would you do? Well, the problem is you've got this path through G that allows you to have a circuit. So if we just cut out G here, then now the current would have to go through A, and that means our B and D would get a touch dimmer, but A would now turn on, and so this would become 3 light bulbs all in series. So yes, that's G. And then which wire would you cut to turn off all of the bulbs? So in this case, I guess you've got some options. Well, I guess you don't have options. You have one option. So in this case, if you wanted to turn off all the bulbs, you would have to cut a wire that connects basically the positive to the negative terminal. So if you cut G, you would still have lights on. E actually wouldn't do anything. C would work. So if you cut C, then there would be no path from the positive terminal to the negative terminal. And if you cut F, there'd be no path to the positive or the negative terminal. So actually C and F here would kill our circuit if we did that. So yeah, so I think I put up some FETs for you guys to work with, so hopefully those help you out. And also there's a FET for the capacitors too that I think I forgot to mention, but that's good too. So yeah, so those can help you out with this. And you've got a couple questions to answer, so I think that's it for our lesson for the so-called Tuesday class. So good luck with the assignment, and take care of yourselves.